All right. Well, thank you for coming. So the talk tonight is about automatic machine learning, and then more specifically how we do automatic machine learning in H2O. And then I'm going to basically just show you how to do that. So if you have your own data set, you can try it pretty easily, hopefully by the end of the night, or it's basically one line of code. So we try to make it easy. So my name is Erin LeDell, and let me just make sure my slides are working. So as Saurabh mentioned, I'm the chief machine learning scientist at H2O. So basically, the thing that I spend the most time on right now is automated machine learning. So we've spent the last basically 6 years since the company was founded in 2012, just building all the algorithms from scratch. And then now we have this large selection of machine learning algorithms and infrastructure around that. And so now we're sort of, ran out of things to do. So we decided to automate it all. Not really, but just makes it, basically we're always just trying to make it more accessible, whether that means providing you access in R and Python to big data, algorithms. That's one way to make it more accessible, but then sort of lowering the barrier to entry in what you have to know about data science in order to do good machine learning. So just in case you're unfamiliar with the company, how many of you have heard of H2O before?
Me.
Okay. One person. No, just kidding. So that was a lot of hands. And then how many of you have used H2O just at some point? Okay, so just not as many people. So AutoML is actually a really easy way to start using H2O because, it's the path of least resistance to getting good models. So then just a little bit more about the company. We're in Mountain View, and we were founded in 2012, and we are advised by, so our academic advisors are Stanford professors Trevor Hasty, Rob Tibshirani, and Stephen Boyd. And so if you've ever seen this book called Elements of Statistical Learning, that's two of these guys are the authors of that. And so we work pretty closely with them to, sort of get advice about, different issues, and basically they're sort of our academic mentors. And then H2O is also the name of the library. So you could call it a library, a machine learning library. You could also call it a platform because it also includes more than just algorithms. It's sort of a data processing library in itself, and a distributed key value store, distributed data frames, all of this infrastructure around doing machine learning in a distributed fashion is provided by H2O. And it's open source, and you can use it from sort of all the standard data science languages like R, Python, Scala, Java. And if you choose not to write code, or you don't know how to write code, or your hands just get tired, you can use the web interface as well. All right, so that's just a high-level overview. And then this is what we're going to talk about tonight. So, and then at the bottom I have, I'll make sure I'm not in the way here. Excuse me. There we go. That's a little bit better. At the bottom there's a URL for where these slides are. So if you want to, download the slides and follow along, or just make note of that for later, there's a link. I'll just read it out in case you're not able to see it. It's tinyurl.com/SFBDS, which stands for San Francisco Big Data Science, which is the name of this meetup, -AutoML. So tinyurl.com/SFBDS-AutoML. So what we're going to talk about tonight is just a little bit about what the H2O platform is, because we're sort of presenting AutoML in the terms of H2O, so it would be good to be a little bit familiar with the platform. And then I'm going to talk about just generally what is AutoML, what does that term mean, and what are all the different pieces and parts of that, and where does H2O fit into that ecosystem, and then I'm going to talk more specifically, like what is H2O AutoML, which is the name of our AutoML tool, and then I'm just going to give you some practical tips on how to use it. It's pretty straightforward, but I'm going to give you some more tips to make that, if there's any questions or, basically how to become a pro user at using this AutoML tool. And then we're going to do, I don't know if we'll do a live demo, maybe we'll just go over some code. And then maybe just now, so I can get an idea, if you have a preference between R and Python, or I guess also I'll include the GUI in that. So if you have a preference, R, Python, or GUI, can you raise your hand if you're R? Okay, how about Python? Okay, a little bit more Python. How about GUI? Okay, it's good to see. I'll show you all of them, but when I do the demo, maybe I'll do Python because it looks like most people are Python. Okay, so let's get started. So H2O platform, this is just an overview of what I said before, a little bit more detail. So H2O contains distributed implementations of machine learning algorithms. So what that means is they are multi-core on your machine, and they're also multi-node. So if you have a cluster, they can run across multiple nodes on a cluster. And that's kind of what H2O was built for. So if you think back to 2012 when H2O started, Hadoop was kind of like all the rage, and big data was all the rage. Now it's AI. Nobody talks about big data anymore. But big data is still relevant. So H2O was really built to be a machine learning library that would scale to big data. And so part of how we did that was scaling it in terms of the cores on your machine and then also multiple nodes. But a lot of people just use it if you're sort of comfortable just using a laptop for data science. That's how a lot of people use H2O. So if you have really big data, you might want to use a cluster. The point is it's very flexible, so you can just use it on whatever size data you have and on whatever hardware that you have. And then all the algorithms are written in Java, but we have APIs, I mentioned, and all the data science languages. And one of the other unique aspects about H2O is that in contrast to some other libraries that are maybe just only in R or Python, when you talk about or when you think about how to productionize machine learning code, some people might productionize R or Python models, but it depends on what your use case is. But a lot of enterprise shops will use Java, and they want basically their models in Java, and so H2O makes that very easy. So you can deploy the models as pure Java code and compile them into your projects. And if you're more of just data scientist, not productionizing anything, you can also just save the models to disk like you would in R and Python. We don't force you to export them to Java code. And then, of course, it works on Hadoop, Spark. If you set up just a regular cluster on EC2 or your laptop, it's meant to work anywhere. And then this is the most technical slide that I have in this whole talk, but just to provide some context, if people are interested in distributing computing and how we do that in H2O, I just want to introduce two concepts that we have in H2O that are kind of just important to understand. Even if you're doing AutoML, it's good to just have a general understanding of what we're doing under the hood, even though you don't really need to know the details. So one thing that we have is we have what's called the H2O cluster, and that's just all that means is it's just a shared Java memory process, basically either on your laptop or across a cluster, across a physical cluster. So H2O cluster just means just some memory where H2O is running. And sometimes people get confused about that. They think that H2O is like on the cloud or something, and when they upload their data to the cluster, it's going somewhere outside of your computer, but that's not the case unless you are the person that's setting up that cluster on EC2 and your data is going there. So that's just to clarify. The cluster is just wherever you put it, and you have 100% control over it, and that's where your data is. There's no such thing as an H2O cloud or any sort of cloud computing component here. And yeah, that's just where everything happens. That's where you load the data. That's where you train the models. It's just, a set-aside piece of memory where everything's happening. And then the other thing is just an H2O frame. And if you know what a data frame is, that's basically what it is. It's rows and columns. With an H2O frame, you can distribute that over a number of nodes. So you don't have to know about that. So that's what's nice about H2O is when you're dealing with the H2O frame, it's just like an R data frame or a pandas data frame. And you subset rows and stuff the same. But what's happening underneath is that it might be that some rows are on this machine, some rows are on this machine, and all of that, magic is happening under the hood. So yeah, that's just what we call a data frame. So, all right, so let's get back to machine learning. So some of the features of the H2O library are, basically we have a bunch of supervised and unsupervised machine learning algorithms, and we've implemented all these from scratch. So we, take careful consideration to what we put in the library because we have to maintain all of this code, and it has to be distributed and it has to be high performance. So we have a smaller selection of libraries than, let's say, scikit-learn, or if you're an R person, it would be caret or MLR. But the ones that we've chosen are, we think the most useful, and also they can scale. And that's why we've chosen the ones that we have. And then a lot of the nice features of H2O have to do with basically pain points that you get if you use some other libraries where you have to do a lot of the pre-processing yourself. So if you have to do imputation, if you have missing values, if you are using certain algorithms, you have to normalize the features. If you're using some algorithms, you have to do what's called one-hot encoding. So if you have categorical data, you have to encode that somehow that a machine learning algorithm can understand. And so this is all kind of like the boring stuff of data science, and we do all of that automatically, so you don't have to think about these things. And I can tell you that once you've been using H2O for a while and you go back to another library, that's like the first thing that I notice is like, oh my God, I'm like writing all this code to do stuff that you have to do every single time, and it's takes away some of the fun. So we try to do that automatically. And then another feature that we have that is useful is something called early stopping. So in some algorithms, they have a tendency to overfit. So if you train them too much or for too long, they can sort of memorize your data instead of learning a useful representation that can be abstracted to new data. So the process in which you stop the learning is called early stopping. And usually you might have to do that by hand or plot out the performance as you're going and then decide manually where to stop. We have something that will kind of do that automatically. So that's also a nice practical feature. And then all the other parts of machine learning that you need, sort of the infrastructure around it, which includes things like cross-validation, grid search, random search, all of these machine learning things we have included in H2O. That's true of most libraries, like scikit-learn has all of this stuff too. That's not super unique, but it's essential to having a good library. And then once you have the models, we have things to look at variable importance, to look at the metrics of the models and plot things. So these are just all the things that you can do with H2O. Any questions so far? Okay. All right, so now we're just going to talk about, now that we kind of talked about what H2O is, let's talk a little bit more generally about what is automatic machine learning. How many of you have heard of this term before? Okay. How many of you haven't heard it, but you kind of might guess what it is? Okay, we'll see if you're right. Okay, so this is a very sort of ill-defined term. It could mean different things to different people, but this is kind of my description of what AutoML, that's the shortened version, AutoML is. And I like to divide it up into the different pieces of the machine learning pipeline. So, and all of these aspects we can do some automation. So generally, just to even get started with machine learning, you have to do some sort of data preparation. You have to get your data into a structured format where you have rows and columns where, maybe it comes from a large database, where a large relational database, and you have to do queries to get it into that format. These are things that you have to do to just do machine learning. So just getting it into the structured format could be part of that. And then also that could include things that I mentioned that H2O already does, like imputation of missing values and one-hot encoding or other types of encoding. And then it could also include things like automatic feature engineering. So once you have your data, is there something that you can do to get more data out of that data? That's an important part of machine learning, and it's largely a manual piece up until sort of recently. So that's what I mean by data prep. And then model generation. So once you have the data kind of sorted out, then you might need to generate a lot of models to sort of make sure that you find a good one. Because a priori you don't know what the right parameters are for the best model, so you have to do things like random search or Bayesian hyperparameter optimization to try to get a bunch of models and sort of with the goal of getting a really good model. And then once you have all these models, probably not everybody would include this part in AutoML, but if your goal is to get the best model that you can get, I think it's important to always use ensembles, which means you're combining different models together. So, that's sort of an optional component, but it depends on sort of what you value. If you're valuing model performance over complexity, that's where you would head. Okay, so this is just a little bit more detail about what these terms mean. So for data preprocessing, I mentioned some of these things that we have already, but then there's things like feature selection or feature extraction. So that would be just, I would include that in data preprocessing. And then different types of encoding of categorical features is also a really important part to getting good performance out of your models. So if you think about, in particular, the case where you have a column that represents something like a zip code, like I keep telling people this example, but I don't know exactly how many zip codes there are. I think there's like 50,000 or something. Does anybody know the number? Well, if you happen to Google it, let me know. I think there's like 50,000 zip codes. So in one column, if your column is zip code, you could have 50,000 unique values. And even though they're numeric, represented by numbers, they're really just sort of not related to each other. You could think about them as like colors of the rainbow or something like that, or animal type, or just any sort of category. So when you have features like that with such what's called high cardinality, when there's a lot of different categories in one column, then most machine learning algorithms just completely fail if that's the case. So they'll either try to expand that data into what's called like a binary representation or one-hot encoding. So it would take that one column and turn it into 50,000 binary columns that each represent whether or not that zip code was the one. So that's, again, then you're just adding 50,000 columns to your data set, which is very, very problematic. Or there's other things that you can do that are more intelligent. So there's all these different types of encodings that are, there's count encoding, label encoding, target encoding. These all have different meanings, and they're just different types of methods of dealing with these problematic types of data. So if you're lucky, you don't have this problem, but if you do enough machine learning and data science, you'll run into this problem eventually. Okay, so like how can we deal with that? So then in model generation, I've mentioned grid search and random grid search. There's also something called Bayesian hyperparameter optimization. So basically what that is you're just, you kind of learn this secondary or, side model that's helping you out to choose the next set of parameters to try. So you just maybe start at random with a certain set of parameters for, let's say, random forest, and then you train a model, you get some performance metric, let's say you measure the AUC of the model, then you give that information to this model over here, which is helping you choose what the next set of parameters that you should try. So then it says, okay, maybe this time try max depth equals 10 and sample rate equals 0.5. And then it's helping you guide you through the model training process. And then you send the result of that model back to it. And it's learning because every time you try something new, it finds out how well that model did. And it learns kind of how to send you in the right direction or how to explore a direction that hasn't been explored before. And so one drawback of that method is that it has to be done in a sequential fashion. So you have to do it one after the other, whereas any kind of grid search, you can train all the models at once and be done. So I wouldn't call it a huge drawback, but it's just something to be aware of, especially if you're trying to do parallelization and distributed computing. And then let me just skip over to ensembles. So there's different types of ensembles. So if you think about maybe the most simple type of ensemble would be just sort of averaging the predictions from, let's say, 5 models together. So averaging could be an ensemble. But you could probably do better than that, because if you have some models that are bad, they're going to bring down the performance, and you might as well have just taken the best model. So that's not really a great ensemble. So then we want to think about different ways that we can combine those models together. And 2 ways that I'll mention. One is called stacking. Stacking also is sometimes called superlearning. In Berkeley, that's what it's called. So it might be relevant if you cross the bay. But yeah, stacking or stacked ensembles is the more common term. And that's sort of my favorite type of ensembling. And what you do there is you use another machine learning algorithm to learn what the best combination of the models is. So there's kind of 2 levels of machine learning happening. There's training what we call the base models, and then there's the meta-learning step where you actually use machine learning to figure out what the best combination is. And you train a model to do that. And then there's another type of ensemble, something called ensemble selection. And that's a little bit different, where you basically you have your set of base models and you just randomly sample from that. And if you basically keep doing that until it starts to hurt the performance. So I think there's kind of 2 versions. One where you sample without replacement, meaning if you use a model once, you can only use it once. And then there's another version where it's called with replacement sampling, where you could possibly randomly select the same model multiple times. So it's kind of this greedy approach of putting models in until it doesn't help you anymore. Okay, so those are just a whole bunch of different topics that would fall under automatic machine learning. And of course, the layer that threads these all together is that you want to do these all automatically. Okay, so let me just show you that same slide, but let me highlight some of the stuff that we do in H2O AutoML as of right now. So for free, you get all the imputation, one-hot encoding, and standardization. All that stuff is already included in the H2O models. So, I didn't have to do any extra coding to get that. It's already there. One thing that we're adding right now is target encoding. So that's very valuable in these cases where you have high cardinality categorical features like a zip code. So that could be extremely useful and will be extremely useful for AutoML. And so that's not highlighted because it's not in the current release, but we're adding it right now. And then for model generation, we basically do a random grid search over all of the models that we have. And I wouldn't say it's completely random, so we've put some thought into which parameters are we looking at and what are the ranges, and that's kind of more the sort of data science domain expertise that we've put into this tool. So that's actually one of the harder parts about tuning models, is knowing which parameters to tune and what values you should look over, and that's it takes a lot of skill as you're train more and more models as a data scientist. That becomes a little bit more routine, and you have kind of a go-to grid search that you might do for each algorithm, but that's, even if you're an expert at tuning a GBM, you might not be an expert at tuning a deep neural network, for example. So it's good to sort of have help or look around to see what other people are doing there and just see what works. So we do that. And then we also tune the models individually using a validation set for early stopping. So for GBMs and deep learning in particular, that's important because you don't want to overfit your models. So we use a validation set to make sure we have not overfit our models. And then with all of those models that we've generated, we do stacked ensembles at the end. And we do 2 different types. Let me see if they're put on the next slide. So I'll explain. We do 2 stacked ensembles right now. One that just includes all the models. So that's generally the one that does the best. But let's say you ran AutoML on your data set for, let's say you ran it for 1,000 models. And so it'll make an ensemble of those 1,000 models. It will probably be your best model, but if you want to put that into production, maybe you want to think twice about that before you need to make, because for ensembles, you need to ask each of the individual models first what their predictions are. Then you feed that into the meta learner, and then it tells you the final answer. So if you're trying to do things very quickly, you don't want to probably have a 1,000 model ensemble. So we have another one that we train as well, which is kind of made specifically for the purpose of production, where we just take the best model from each algorithm class. So we take the best GBM, best random forest, and we just make a little simple ensemble there. And generally that's maybe the second best model of all your models. So still really good. You get some of the performance benefits of using ensembles, but it's also pretty lightweight that you could still put it into production. Okay, and so why do we take this approach? Well, there's a couple of reasons. One, we use what we already have in H2O. So this is, we have random grid search, we have stacking, and so we want to make sure we utilize best what we already have. But also because these 2 things work really well together. So stacking works particularly well when you have a diverse set of models. So even if you have like a GLM that's maybe not doing so well, or maybe a deep neural net that's not doing so well in comparison to your GBMs, putting them in the stacked ensemble most of the time helps. Every once in a while, you can kind of shoot yourself in the foot by putting in a really bad GLM. But in theory, that's what stacking is good at, is ignoring the bad models. So in general, it's still good to put them in, and you can try it out. Like you could try training stacked ensembles where you put in some of the worst models and then try where you don't, and then compare and see how they do. So usually the extra diversity actually helps the overall performance of the ensemble, even if they're not so good. And I see sometimes people make the mistake of trying to make an ensemble with just maybe the best models that they have. And they might all be very similar. Maybe they're all GBMs. And so then you still get a little bit of a boost over your best model, but you might do better by just putting in everything that you have, or at least something from each algorithm category that you're covering. So the reason that, I guess from a statistical perspective, why this works is, so stacking does well when the models make uncorrelated errors, meaning they fail in different ways. So there might be some data points where you make a prediction and sort of these models over here do better than these ones, but overall these ones do better. Like it's very kind of mysterious how data is sometimes. So maybe your data set is not super homogeneous. Maybe there's kind of some different subsets of your data that do better on certain algorithms, and stacking helps deal with that situation. So the one way to get models that are diverse is to just randomly generate them. So that's what random grid search does. So these 2 things work really well together. And this is kind of what our AutoML is based on. So this is just an overview of of what I just said, but just kind of more succinctly. Yeah, so I've said all this, and then basically it goes through, trains all these different grids, and then does the stacked ensembles, and then what you get back from AutoML is you get a leaderboard, something that we call leaderboard. And so how many of you are familiar with Kaggle? Okay, a lot of you. But those of you who don't know what Kaggle is, it's a website where people compete in data science competitions. And so it's pretty fun. And basically, you form teams or you play by yourself, and there's somebody, generally a company will sponsor a competition, and they put up a data set for some problem that they're trying to solve, and then everybody tries to get the best score, basically. And so then you get all ranked on this leaderboard, and you see all your models up there, and it's this, sort of competitive approach to data science. Yeah, and so that's why we call it the leaderboard. So let me just show you now, like what does the interface look like? So this is called Flow. So this is the GUI for H2O. So anytime you start up H2O, it will also start up a web server that's running this GUI, basically. And so even if you're using R or Python, you can always switch over to the GUI. You just type in the right, IP and port into your browser, and it will pop up this little window, and you can do everything by clicking around. So you can load data sets by clicking. You can train models by clicking. And so if you want to, limit your carpal tunnel syndrome, then you should head over to AutoML, because there's the fewest number of clicks required to train models. So basically, you upload your data, you click on the AutoML button, and it pulls up this interface where you probably can't see it very well from that all the way in the back, but if you have downloaded the slides or you might look at them later, basically what you'll see here is a bunch of fields. So one of them is called the training frame, so you just have to select which data set you're looking at, and then once you load training frame in, you'll then see the column list, and then you can tell it which column are you trying to predict. And then there's actually more fields here than you really need to deal with. So in Flow, it exposes all the fields that we have available. But generally, with AutoML, you basically just have to say, here's your data set, here's the column that you're trying to predict, and then how long do you want this to run for? So you can control that by the number of models that it trains. So you could say, run this for 50 models, and then stop. Or you can run it by time. So you can say, train for an hour, and then stop. And then there's other sort of more sophisticated methods where you can tweak the early stopping parameters. So basically, if you said train for 24 hours, but I want you to stop when you stop seeing a big improvement in the models, that's another way to use it. And then you would tell it which metric that you care about. So we would assume certain things based on your data. So if you have a binary classification problem and you didn't tell us anything else, we would just try to optimize for AUC. But if you wanted to optimize for log loss, you would just put that into, the thing here. So there's a parameter called sort metric, and that just, how do you want to sort the leaderboard, basically, is what that's asking. And then for the R people in the room, this is what it would look like. So this follows the general H2O interface. So you load the library, and you always have to start up the H2O cluster. So that's the sort of unique, that's why I mentioned what the H2O cluster is, because you kind of just need to know that there's one line of code that you need to add to do that. So you initialize the cluster, then you might import your data, maybe from a CSV or from a variety of other places. Import file will import data from a lot of different formats. If you have data in HDFS or on S3 or a Avro file or an ARF file or all these different formats we support. So that you load your training data, and then you specify these few things that I mentioned that you need to do. So you have to tell it what your training data is, then what the name of the column that you're trying to predict is, and then In this case, I'm saying run for 10 minutes and then stop. And then once you're done, what you want to look at is your leaderboard, and I'll show you a picture of what a leaderboard is in a minute. But first, let me just show you the Python version, since there's a lot of Python people here. So same idea, just one extra line of code, because this is a little bit more Pythonic, the way that we set it up here. So we create an object of type H2O AutoML. So then we sort of initialize that object, and then we call the train method to actually start the training. And so we sort of separate the two things there. And then once you're done, you can look at the leaderboard. And I think that'll be my next slide. So here's just an example of what a leaderboard is. So it's really just a data frame that has the names of your models in there, and then the performance metrics. So in H2O, everything has an ID. So this is how we distinguish models from each other or data sets from each other. So these are all the model IDs. So if you wanted to go and look at these models and examine what the hyperparameters are, then you just grab the model by ID, and then you can look at it and do all sorts of things with it, or take it and put it into production, or whatever you want to do with it. So in the leaderboard, we just sort of give you the metadata. So what's the name of the model? And we auto-generate these names. So at least you'll know what model types they are. So you might not know from looking at this ID what the parameters are, but you know it's a GBM, and then another GBM, and a few more GBMs. This is an example, like a real example, on a data set called Higgs, which is a sample binary classification data set where you're trying to predict basically whether or not, I think it's a simulated physics data set where you're trying to predict like something about the Higgs boson. But it's just an easy example, so I use it. And so yeah, this is a real example. So you'll see at the top, the best model here is the stacked ensemble with all models. And you probably can't see that AUC at the back, but and if you're not sure what AUC is, it's just a metric that we use for binary classification. And the higher, the better. So it basically ranges from 0.5 to 1. So 1 is perfect. It probably means you have overfit or done something bad, but 1 is what you should be trying to aim for, and 0.5 means it's essentially no better than flipping a coin, and your model is complete garbage. So, something in between there is good. And so this stacked ensemble at the top got a 0.788 AUC, and then the next one below had a 0.783, and then the top GBM had a 0.780. And then those of you who are familiar with Kaggle might have some sense of what this performance gain is, because on the Kaggle leaderboard, you'll see, you'll go out to like 4 decimal places, and it will be like 100 slots on the leaderboard. So people are just fighting over those 4th and 5th decimal places to win. So this is actually a pretty significant improvement from this single model to the stacked ensemble in that context. And of course, all of this all of this is connected to whatever your business problem is or whatever your science problem is. That difference may or may not matter. Maybe it means the difference between saving $1 million on a fraud problem, or maybe it's not significant at all. Yeah, question?
How do you translate your business problem into AutoML?
That's a good question. There's not like a simple answer to that. So the question was, how do you translate your business problem into AutoML? So generally, in terms of like, if you can formulate your business problem as some sort of binary classification problem, that's the first step, is saying, let me predict, fraud or customer churn or something like that. That's a binary classification problem. And your goal then would be to choose the best model. I mean, I would probably choose, it doesn't matter if you choose AUC or log loss. So I'll give you one tip. So basically, if it matters what if all you care about is making that cutoff between yes and no, or fraud and not fraud, then you probably want to use AUC, because AUC helps to basically separate those two classes. Like if you have a good AUC, it means you're separating those two things pretty well. But if your goal is to make meaningful predictions about what the value is that in some sense correlates to like the probability of fraud, then you probably want to use something like log loss, because it's better at dealing with, I mean, this is like all like hardcore data science stuff. So just knowing which one to use is also a data science problem in itself, which is why we try to just give you one that we think will make sense in the most cases. And I did a Twitter survey, which is a very scientific way to gather data these days, but I did a Twitter survey to figure out which one of these two metrics, there's other metrics that you can use, but these are kind of the two main ones, which is more commonly used in industry, and it was like people use AUC 3 times as much as log loss. So it's not why I made the decision to do, to default to log loss, but confirmed a hunch that I had. So yeah, so it's in some cases this translates to actual dollars, so that's a lot easier, especially if you're doing a regression problem where you're actually predicting costs and stuff like that. It's very easy to understand. If your model is this much off, it's equal to that many dollars. So and if you can kind of narrow that gap, it's helpful. Yeah, did you have a question?
Is there a way to optimize for anything else, like the best precision?
So in H2O, we have a predefined set of metrics, the ones that we think are important, or I guess most commonly used. And so one of the metrics that we calculate is precision, recall, we do all of that as well. Right now, you can't optimize for precision or recall in AutoML, but we'll probably add that. So we'll first basically there's a few metrics that we don't have yet, which are they're there and they're just waiting for us to add them. And then the extension of that would be allowing people to write their own custom metric functions. So it's a little bit difficult to do that in H2O because everything's in Java. So unless you want to write Java code. So basically we made, and I haven't tested this out myself yet, but we made this, we have this ability now where you can write a Python function and you can point, I think this is maybe only for GBM, but I'll have to look into that. But basically we've exposed it so that you can write your own Python function and we will sort of turn that into Java code automatically and handle that for you. Because we have had that request, could I write my own custom loss function? And some algorithms support that, like GBM is an algorithm which can support any loss function, basically. You can just make something up. Other algorithms internally have metrics that they use and they're kind of harder to decouple. But GBM is one where you can very easily decouple it, and it's just a matter of writing the software to do that. So hopefully in a future version, we can utilize that functionality in H2O to, at least in Python, write. I don't know if we'll do it in R too, I'm not sure what the plan is for that, but that would be a nice feature, yeah. Any more questions? Yeah.
Is there a predefined way to handle unbalanced data sets in the AutoML?
So the question is there a way to deal with imbalanced data sets in AutoML? Yeah, so there's currently what we have is in all the H2O algorithms, we have 3 parameters that help to handle imbalanced data. So one is just a flag that says balance classes equals true or false. So if you just set that to true, then we will do something automatically to balance the classes. And then the other 2 parameters control what that something is. It's like, do you want to multiply it by this amount? And then it puts limits on how big the data can get and things like that. Because if you have, let's say, 1% and you want to balance it, then that's going to expand your data set quite a lot. And so maybe you don't want to fully balance it. So we have 2 other parameters that you can tweak to control that. And in AutoML right now, we have those parameters exposed. So you can set them yourself, and now there's a ticket that will do that automatically if we see that your data set is imbalanced. So that will be just something we'll add soon, basically. Right now, people were just asking for us to expose those quickly, so we just added them so that people have that access if they need it. And then, yeah, the next phase is just to come up with a reasonable way to just set those automatically. Yeah.
This is a very basic question.
Sure.
The GBMs on your screen right now, could they be the same GBM model or algorithm executing against different parameters, or might they be different implementations of GBM?
That's a good question. So he's asking, are the GBMs the same GBM algorithm, or are they different implementations? So these GBMs here are all the H2O GBM. But another thing that we're adding right now, and we had a big meeting about this today, is we're adding XGBoost. So XGBoost is another GBM implementation that's very, very popular, and it's used on Kaggle all the time. And so I don't know how long ago, but maybe like 6 months ago, we added XGBoost into H2O, because that's the beauty of open source. If, you know, there's no sense to compete, in a sense, with XGBoost. You just add it in, and then it just adds to the richness of the H2O library, so that you basically can do all the same, you know, grid search, metrics, everything using XGBoost. So now XGBoost has been in H2O for a little while, and it took quite a bit of work to get that in there. That was the first third-party library that we integrated into H2O. And you know, we've been working on performance and just optimizing things. Like today, I think we figured out how to speed up the prediction time for our XGBoost models by like 25 times. So now it's actually faster than the regular XGBoost. So that was a big. So we've been working on like little performance tweaks like that. And now that we feel that it's ready, we're putting it into AutoML. So that's another thing that will come out in the next version. So you'll see, we'll call it XGBoost, so it'll be obvious. So you'll see XGBoost on the leaderboard too. Yeah.
So most of your algorithms are in Java land, but XGBoost is like in C or C++, right? So
Yeah.
Can you talk a little bit about like how you're bridging those worlds, like what your plans are for H2O?
Yeah, well, that is what made it a little bit more difficult, is that it's a C++ library, so it's a lot easier to integrate a Java library. So we have talked about, so Light GBM is another GBM library that people like, and we've talked about that, but XGBoost itself has a certain set of parameters that you can tweak to sort of turn it into Light GBM. So we've right now are taking that approach. So we're kind of supporting both libraries. I think if we add more open source libraries into H2O, it'll be things like Bayesian hyperparameter optimization library or something like that, because I would like that for AutoML. In terms of other algorithms, if they're as good as XGBoost, we would definitely add them in. But there's not a lot of other libraries that we see that we're like, we have to have that. So do you have a suggestion of anything?
I guess I'm just trying to more understand the architecture.
Oh, how we do it?
Yeah, because if they're in two different, underlying runtimes, is there a potential that you guys might integrate with like TensorFlow in the future?
Yeah, good question. So, well, I mean, the hard part is having to do with memory allocation. So that was some of the stuff that we spent a lot of time on. So you're kind of asking, well, one library that he mentioned was TensorFlow and whether or not we would integrate that. So we did have this project that we called Deepwater that did integrate TensorFlow, Caffe, and MXNet, which are three deep learning libraries. Because we have a deep learning implementation of a particular type of neural net in H2O, but it's not as expansive as what you would get in TensorFlow or Caffe or these other libraries. So we actually tried to do that, and it worked, but we, after sort of working on that for about a year, we thought it's actually better for people to use Keras instead of Deepwater. So we just that would be our suggestion, basically, is if you want to, because I guess the problems that those types of deep learning libraries do well on are kind of adjacent to the types of data and problems that GBMs and more structured data machine learning algorithms do well on. So it's almost like a whole different set of users and use cases. So deep learning, TensorFlow is very good at, like, if you have image data or speech data or in a lot of cases time series, like text can be treated as like a time series, like a sequence of words. So that's very different than what you have in like traditional business, like tables with rows and columns. So I think, yeah, that's what we've been telling people, is that we did integrate them all together, and it was really complicated, and TensorFlow was changing too quickly, and it was just, we didn't feel that we could compete with Keras or any sort of other library that's sitting on top of TensorFlow and these other things that make it easy to use. And so that's what we tell people, is that, we could give that to you, but we think that we would be better serving you by telling you to use a different library. So, yeah. Sure. So yeah, FastAI. So that's a library on top of PyTorch, and there's a course called fast.ai. Well, it's a website and also a training course. And so that's sort of like, I would say, more equivalent to Keras on top of TensorFlow. So it's just another library that has a lot of like nice user-facing functions that make it easier to use PyTorch. So I don't think we have any plans to do anything with it, but I think it's a good library. Okay, let me just check the time, and then let me move on, and then we'll do more questions. Okay, so I might kind of skip through this a little bit because I have a lot of pro tips in here, but you can maybe bookmark some of them for later. So this is like before you start up a giant EC2 cluster and spend $10,000 because you train 1 million models. First, let's teach you how to do this so that you don't get disappointed. So there's just a few. I mean, it's pretty straightforward, but there's a few things that we like to tell people just to make sure they understand what's going on. So there's an argument called the leaderboard frame, and we don't recommend that you use that unless you know that you need to. And what that frame is, it's just if you want to specify a test set in which you score the leaderboard on, you can pass along a data frame. But we prefer that you, well, I guess I'm not personally invested, but it's probably better to not use a piece of data just to score the leaderboard frame, because if you don't set that, we will just provide you cross-validation metrics. So we're being more resourceful and efficient with the data that you have if you don't pass a leaderboard frame. So we would say, sort of ignore that argument if you see it there, unless you have a specific reason and you want to score on a particular data set and there's some context around that. So don't use it unless you know that you have to. And then if you provide the training frame, part of what we do is we need a little piece of your data to function as a validation frame. So when we're tuning and making sure we don't overfit. So if there is a validation frame argument, so you could pass that on your own if you want to specify that specifically. But if you don't, then we'll just chop something off for you. And right now we choose to chop off 20%. I'm probably going to change that to 10%. I feel like it might be too much. So just so you know that that's happening automatically under the hood. And so right now we just will train all the models that we have in AutoML. And if you're more of a sophisticated user and you have a preference for certain algorithms, you can turn on and off different algorithms. So if you want to turn off the GLMs or the deep learning and just do tree-based algorithms, you could do that. Or conversely, if you have like really wide sparse data and you maybe just feel that GLMs or deep learning are better, then you could go ahead and turn off GBMs and random forest. So that gives you some tunability. So with AutoML, we want it to be a tool for everyone. So that would include advanced users who know maybe more about what they want. And so we want to expose everything, but give you really good defaults so that you, so that if you don't know anything, you can just use it and not have to think about it. Or if you want to kind of have more control, you can do that too. So that's the exclude algos. Yeah.
And maybe I missed the point, previous slide, which first point.
Yeah.
So how did you inspire this workflow where you have training and you just at what point do you then evaluate or test data?
So you can still evaluate on a test set, but you could do that after the fact. So you could do the whole AutoML process and select the best model based on cross-validation metrics, and then you could take that model and then score it on a separate test set if you wanted to do that. So there's no preventing you from doing that. We're just saying you don't need to necessarily chop off a whole piece of your data just to rank the models on the leaderboard to choose the best one. You could just use cross-validation metrics because by default, we're going to do cross-validation anyway, unless you turn it off, and then you would need a leaderboard frame, but we would chop that off automatically. Because you can turn off cross-validation if you're, if you have a billion row data set and you don't really feel like doing cross-validation, maybe you just want train and test or train and validation set, or maybe twofold cross-validation. So you have the ability to turn that off. We'll do fivefold cross-validation by default. All right, so, and then just some things to be aware of. The default for the runtime is 1 hour. So if you just run it without doing anything, it'll run for an hour. So you probably, won't get fired for EC2 bills from that alone. So that seems like a pretty safe number. But basically, the default is set to 1 hour. So if you use the max models parameter to say only train, 10 models or 30 models, and you don't change that 1 hour limit, it'll stop like the first time it hits one of those two things. So if you said, I want it to train for 100 models, but maybe that takes 2 hours, and you don't change max runtime, it'll still stop after an hour. So you might be wondering, hey, I thought, I asked for 200 models, why did it only give me this many? That would just mean that you should change max runtime to something very large so that you don't hit that stopping point. So these are just things that, if you use it a couple times, you'll figure it out, but you might be like confused about why you get certain results. And then just a reminder that all the H2O models are stored in the H2O cluster memory. So if you are going to run it for, 2 days or something and train 1 million models or whatever, you need to have enough memory to store all those models. And we just made a change where by default, we don't store the cross-validation models anymore. We throw those away because that was, that's a lot of extra memory if you're storing the single model of training on the full data, but then also all the 5 cross-validation models as well. So we changed that so that it, by default, doesn't store those extra models that you don't really need per se, but you can turn that back on. But just we're trying to do things that sort of clean up after ourselves for the stuff that we don't need, essentially need.
Couldn't you just cache that?
So the question is, couldn't you just cache that? You could, yeah, but we could add some code in AutoML that would write all those models to disk after it trains them and then throw them away. That could be, a new feature. It'd be probably, these are things that we'll, look at as we find people bumping into things. It's like a good idea. And then, by default on H2O, at least, I actually just discovered this difference last week. There's a difference between R and Python in the H2O init. So R will always default to just a 4 gig heap size. So you're giving it 4 gigs of memory unless you say something bigger, like in this example, like 80 gigs. And that's kind of just to give people, I guess just not to screw up anybody's laptop, basically. If they're running it and they, goes to all of your memory by default and you're like, I hate H2O, it makes my computer so slow all the time. We don't want people to think that. So we just give it like a reasonable, small heap size. And then if you have bigger data, you might want to change that. But I did discover that in Python, it doesn't actually do 4 gigs. It does like 20% of your total RAM is the default or something like that. And those shouldn't be different, but they are for some reason. Because we do like to keep the experience like pretty much identical in R, Python, and across the board. And that's probably a smarter default, actually. So it just has to do with how the R API is generated. If you hard code a default, it's in Python, all of our defaults are like none, and so then they ask Java what the default is, and it gets filled in. It's just, anyway. Another question.
Are you using another technology, an R library to distribute R?
No. So you should think about both R and Python as just sort of an interface to H2O, and no data, none of that is actually in R memory, and there's just one R process that's like your doorway into H2O running on a bigger cluster. So if you try to do things like use an R parallel library with H2O, like bad stuff will happen. So we'll try to create lots of versions, and then we've had people report that things get bad, basically. So they're trying to parallelize it themselves, but we've already done that, so yeah.
So syntactically you support R, but I don't know whether it's H2O.
Yeah. Okay, so let me just check on the time. I think we're at about an hour, so let me just show you the tutorial. So I'm just gonna walk you through some code real quick. So this is the AutoML tutorial that I gave at H2O World in December. So this is kind of like the intro AutoML tutorial that I always show people because it's in both R and Python. So if we go here, so this is a great place to get started. So if you have a preference for binary classification or regression, we can do both. And I think I'll just do binary classification because a lot of business problems are that. And let me click on the IPython notebook, or the Jupyter notebook, I guess it's called now. So yeah, this I'm just sort of showing you this so you know where to go when you want to try out H2O. So because I've shown you the code basically that how to do AutoML, it's not that big, but this will just walk you through a whole problem where you download this data set that's this product backorders data set. So the goal here is to predict whether or not a product is going to be on backorder. So that's a binary classification problem. And then you use some features that have to do with things like current inventory, transit time, demand forecasts, and prior sales. So just this is kind of like a pretty toy problem, but it gets the message across pretty effectively. So we're going to just load the data. This is a very sort of complicated set of code just to load a data, but this is because we were running this in Docker, and we want to make sure that we pull from Docker, because when you're at a conference and you try to do a demo or workshop over the internet and require everybody to download a data set, that just never works. So anyway, this code looks to see if it can find the data set locally, and then if it can't, it pulls it off the internet. That's why it looks complicated. But really, this should just be a string of where your data is. And that's just a look at the data. And here we have an ID column, which we just decided to remove because that's not going to be predictive in any way, and it might actually introduce leakage. That's another topic that we could talk about later, but basically here you go. We're just training AutoML for 10 models. And then we look at the leaderboard. And I think since I committed this IPython notebook to GitHub, we now have extra columns here. So I think we just started with AUC log loss. Now we have a few more metrics of what we already have included in H2O. So you'll see more columns there. And this is just showing you the leaderboard. So in this case, the stacked ensemble with all the models did the best. And then this is a case where it's not always that the stacked ensemble with one of each is the second best. So that's not by means guaranteed that it's always going to be the second best model. Hopefully, it is. And in this case, they're not too far apart. But and I guess I shouldn't say hopefully. It doesn't really matter. I'm not super emotionally attached to a stacked ensemble winning, but a little bit. So yeah, this will just show you some models. I think we somewhat deprioritize deep learning models because we find that they, on a lot of tabular data, don't do that well. So if you notice that there aren't any deep learning models in your leaderboard, let me see if there's, yeah, there is. So this, by default, I was just showing the head, but if you print it out, we actually just had one deep learning model. So we do basically allocate time based on what we think is going to be useful. So we spend more time in the GBM space than we do on deep learning, for example. So that's why you see one deep learning model here. And it's not fair. If we did spend a lot of time on deep learning, we would get a better model than this one here. It's just not a great model. So, but probably still adding that to the ensemble. So actually, this is a case where maybe this is hurting the ensemble because it's so much worse than all the other ones, which is maybe why we're seeing this here. Yeah, so it's just something to be aware of. And of course, you can use the stacked ensemble function to kind of make your own custom ensembles if you want. So after you ran AutoML and you see all these models, maybe you want to do some more experimentation, or maybe you want to run AutoML for longer and get more models and combine them in different ways. You can do all that. Yeah?
Is that a piece of generally accepted wisdom that tabular data and deep learning may not go together very well?
So the question is it accepted wisdom that deep learning and tabular data don't go well together? I think it depends who you ask. I think, and it depends what kind of deep learning you're talking about, and it depends what libraries you're using, and it depends how much power you give it. So if I were to run, maybe the FastAI library or PyTorch or TensorFlow on a bunch of GPUs on this data set, it might do okay. But you generally have to put more effort and more power into getting equivalent performance. And then sometimes it just doesn't work. And one of the reasons it doesn't work is there's so many different ways to build a deep neural network that it's very difficult to get it right quickly. So if you use a GBM or a random forest, it's much easier to get to those good models quickly, whereas maybe deep learning could get there, but you might spend a lot more time getting there, and you might have to know a lot more about deep learning and neural networks to get there as well. So, because there's all different architectures and things like that. So yeah, deep learning definitely is best for image and data and highly, I don't know what the word to use is, but basically data that's not independent. So these are like all the features are sort of supposed to be independent from each other with regular machine learning. And if you take something like an image, like the pixels over here are very much related to the pixels over here, and like it's just not fitting that normal statistical machine learning definition, and that's part of the reason that that you have to construct these more complicated structures to handle that. Yeah, you're welcome. So yeah, let me just, oh, and then I'll just show you one thing, just because one thing I think is interesting is ensembles. And so we could look at, so what does the stacked ensemble think is useful? So, so you could look at the leaderboard and kind of get an idea, like this one's good, then that one, then this one, then that one. But how the stacked ensemble uses those models might be a little bit different than how you see them appear on the leaderboard. So what we can do is look at, in this case, by default, our stacked ensemble will use a GLM as the meta learner, which is the algorithm that combines the base learners together. You can use other ones. You could use deep learning. You could use GBMs. It takes a little bit more time to get those right. So GLM is kind of the easy, does a really good job with minimal effort version. So that's what we use by default. And so because it's a GLM, it's just giving you a linear combination of the base learners as your prediction, so you can see how they weight the different learners. So here I'm just looking at the, so if you think about what this GLM meta learner is doing, the input data is the predictions from the base learners. So if there's like 10 models in your ensemble, you have 10 features in your training data for the meta learner. And so your features are actually the base learners here. So this will show you just the standard coefficient magnitudes for the meta learner GLM, and the one that it thinks is it's weighting the most is this one that we call XRT, which actually stands for extremely randomized trees. So this is just a version of random forest that we like to use sometimes. It's more random than random forest. It's extremely random. And it does pretty well on this data. And then this, GBM here, we could look at the parameters and look more closely to see what that is. And then we have another GBM, and then the regular random forest, and some more GBMs. And then towards the bottom, we see, deep learning. I guess I just sort of had a theory that maybe deep learning was hurting the model, the stacked ensemble, the second one. But in this case, the all model stacked ensemble, it's completely ignoring the deep learning because it's learned that that's just not giving anything good. And then this random GBM on the bottom here that, we trained, we're doing random grid search. So whatever, this GBM got for hyperparameters, they were not very good. Just a random selection, and they just happened to be very bad. So it's ignoring this GBM too. So that's just kind of an interesting sort of look inside of a stacked ensemble. And then, of course, these are all just H2O models, and so you can save them to disk. You can do everything that you do with like a regular H2O model. And then we'll automatically designate the model that is at the top of the leaderboard to be the leader model. So if you just did save model on an AutoML object, it would just grab the top model. So, but you could also grab other ones out of there and save those too, however you want to do it. Okay, so that's just kind of a short demo, and then I'll just, go back. I think I have just a bunch of, I'll just wrap it up now. So here's just a bunch of resources to learn more about H2O. The AutoML user guide on our documentation site is good, so that's a good place to read more about AutoML. And we have tutorials, so I showed you the AutoML tutorial. Then all of our slide decks, like for meetups, we put in this repo here, so including this, this slide deck will also go here, and that tiny URL link that I gave you just redirects to this meetups directory. And then we have videos. We record a lot of our videos, Stack Overflow if you have questions. We also have a Google group, which we've had for sort of since the beginning of H2O, but I think Stack Overflow is a better way to get your questions answered. This thing called Gitter, I don't recommend really using that. It's more, I guess it's just another place that you can find us. But it's better to use Stack Overflow, I'll just say. We're more responsive there. And then to find out about more of our meetups, we have this event page. And then if you want to contribute to H2O, and you could, if you're R, Python, Java, whatever, there's all different ways that you can contribute. If you want to just help with examples or documentation, get in touch or read through this contributing guide. And then I think if you want to find me elsewhere, and that's my handle on GitHub and Twitter and my email address, so you can get a hold of me there. All right, so I'll just save a little bit of time for like 2 questions. Yeah, in the back.
Let me bring the mic. How would you explain how this AutoML intersects with your guys' driverless AI thing you guys have been starting to talk about?
I should definitely mention that. So driverless AI is a proprietary tool that we have, and it's also an AutoML tool. So the main difference, there's a lot of differences that where driverless has more features, but the main difference from a machine learning perspective is that driverless does a lot of automated feature engineering. And AutoML doesn't really do automated feature engineering. We are going to be adding target encoding, which will help. So that is, some automated feature engineering, but that's really where they diverge, the 2 tools, and where you get more predictive models. So the modeling aspect of driverless is similar to AutoML. We do ensembles and we do that type of thing. But the data that you have going into the models is enriched by the driverless AI process. And we basically, we hired a bunch of Kaggle grandmasters who know how to do this like highly sophisticated feature engineering tricks that they, get up to the top of the leaderboard on Kaggle, and they've figured out a way to sort of automate that. And that's the main difference. So yeah, and you can download driverless and try it out. I think we have a trial license, for 3 weeks or a month or something like that. So if you had a data set and you want to compare, you could try that out. Yeah, another question?
Yeah, I like your product very much because I follow your company since 2013 when your company started in a small apartment in Multimedia. And I have downloaded your driverless AI and tried it for 3 weeks. But it's only once a lifetime, yeah. So, and I like that, and it's very easy to use, and I can download the code like that.
Yeah.
But my question is, how can I use the experience and the skill I learned from your product, and to secure a job, in big company or secure a consultant, project, yeah.
Good question. So so basically, how do you market yourself as someone who knows H2O products to get a job? And I think like the first step would be just search in the job posting sites for H2O or driverless. You probably see more H2O because it's been around longer, but we see a lot of jobs advertising specifically for H2O, and they might say things like needs to know Spark and H2O and blah, blah, blah. So those would be the jobs that I would target because those are the people that are obviously looking for that skill. And then, if you're interviewing at, if it's a company that has like structured data and you're doing data science on that, then they probably expect you to know some tool. So maybe they, expect you to know scikit-learn or H2O or whatever. But certainly it'll be more useful to a company that's already using H2O and, because, it's not that hard to go from one to the other, but if you have the knowledge in H2O, I think finding those companies that are looking for that is like the main way that I would say to go about that. And then you could just show them like what you've done and show them about AutoML, and then they'll know that you're on the cutting edge. Okay, one last question, anyone? Okay.
It's very good price.
Okay, thank you. Yeah, he said H2O is a very good product, in case you didn't hear.
Yeah, easy, you know.
Easy and great.
Thank
Thank you. You know, we didn't pay him, we just gave him some people. All right, thank you.